Thank you all for joining the AP Calculus APUBC Unit 6 review. First of all, disclaimer. AP is a trademark registered by the College Board, which is not affiliated with and does not endorse this resource, nor is the 5.5 team. Here's some information about 5.5. I believe you should have seen this multiple times now. This review session was prepared by reading as part of 5.5. Led by Lance, 5.5 is a volunteer student initiative with more than 70 volunteers and more than 10,000 combined volunteer hours that seeks to provide resources for students taking AP courses. Consider checking out our website, 5.5.org, for additional AP resources and practice exams. If you'd like to contribute to 5.5 by creating resources, hosting lectures, or promoting this project, please check out the application document for more information. We review applications on a rolling basis. By the way, can you hear me clearly? If you cannot hear me, you might need to check whether you are deafening. Anyways, let's get straight to this. So you're allowed to ask any questions at any time. You can participate in activities using chat. And by the way, please use bullet type for answers. And please fill out this 5.5 lecture feedback form after you leave. It will greatly improve my lecturing skills. Here's our table of contents for today. For integration, we'll start with accumulation of change and unit sums. Then we'll go through two fundamental theorems of calculus, and then we will have definite and indefinite integrals, and we will do a couple game. And then we'll go to some BC-only integration techniques. After that, I'll have a list of additional resources and a question and answer at the end. The first topic is accumulation of change. This is as the area of the region between the graph of a return function and the x-axis gives the accumulation of change. Sometimes you can use geometry to evaluate. For example, if the real change function is y equals to x, which is a very basic one, and I was told that I want to find the area under the curve between the y-axis, x-axis, the y equals to x line, and this line, x equals to, let's say, 5. Then I can use the area of the triangle formula to get the area, which is 5 times 5 divided by 2, which is 25 over 2 for the area. The area of the region is the unit for the rate of change multiplied by unit for the independent variable. So we can multiply new units. Next, we need to go over Riemann sums. This is a lot of text. The main words is partition and regular partition. For partition, I can divide it into subintervals of varying width. So as long as this is satisfied, then it is called a partition. For regular partition, the subintervals must have the same width. Riemann sum, a regular partition can make the work a lot easier since we have the same width, but you can choose not to have the same width, and that will work as well. Let's look closely at some special cases of Riemann sums. We have the left endpoint approximation. To approximate the entire interval. So what this means is that we use the left endpoints to approximate the area. So it can be visualized by those rectangles. So we pick the left endpoints to approximate this entire integral. Left endpoint approximation in this case. Right endpoint is very similar, but this time we pick the rightmost point instead. So we pick fx1 for the interval x0, x1. So use that function value to approximate the entire interval. And visually, it might be better to see it visually. So we pick the right endpoint for the rectangles. Midpoint, it is also quite similar. Instead of picking the left endpoint or right endpoint, I pick the middle. So here, I pick the middle value instead of left or right. Last one is trapezoids. This time we construct a trapezoid using the two bases of the function value. So visually, for interval like this, suppose this is one interval, the trapezoid is constructed by the base. The first base is the leftmost function value, and the second base is the rightmost function value. The height of the trapezoid is the width. We can use the trapezoid formula, which is the sum of two bases times height divided by 2. That's why we have this formula. And if you add everything together, we have this summation notation. Sometimes we can use graphing calculators, such as Desmos or TI-84. You can also use other types of graphing calculators as well, but these two are the most common ones. On Desmos, it is easier. So suppose I want to evaluate this interval, and I put it into a graph in decimals by inputting int. It will give you the symbol, and then you can put all those extra things in. It will give you a value immediately. And we usually round to 3 decimal places. For TI-84, it is a bit more complex when you pick the option 4 out of the list, and it will also give us an integration sign. Show it quickly here. So we need to hit alpha F2, select option 4, and then we get an integral. This again in the normal. Alpha F2 4, and I can get an integral 0 to x squared plus 3x and dx. And then I get a value just like this. It is also important to check whether you are overestimating or underestimating. If the function is strictly increasing, then this means that we're picking, for left endpoint approximation, we're picking the smallest value of the entire interval. So we're underestimating it. For example, this function is strictly increasing. So I will have intervals like this. And I'm clearly underestimating because because the left endpoint is only covering those areas. Missing a lot of area here. For right endpoint, I will overestimate because I'm picking the largest value out of each subinterval. A similar strategy applies for strictly decreasing functions. If we're picking left endpoint approximation, we're overestimating because we're picking the highest value out of the subinterval. Like this. Of those extra areas. But if we're picking the right endpoint for a strictly decreasing function, then we are underestimated because we're picking the smallest value out of the entire subinterval. For trapezoids, if it is concave up, it's concave down, but if it is concave up like this, for a trapezoid, I have those trapezoids. If it is concave up, I will overestimate because I have those extra areas. If I'm concave down, I will underestimate the value because I will miss those areas. So these are some helpful information to know about overestimation versus underestimation. With that, let's look at an actual exam effort key and calculator active so we can use graphing calculator. We have a table of values with R as centimeters and FR as milligrams per square centimeter. The density of a bacterial population in a circular petri dish at a distance R centimeters from the center of the dish is given by an increasing differentiable function f, where FR is measured in milligrams per square centimeter. Values of FR for selected values of R are given in table above. We're only going to do part B and C. Well, for part B, the total mass in milligrams of bacteria in a petri dish is given by the integral expression 2 pi, the definite integral from 0 to 4 RFR dr. We want to approximate the value of it using a right Riemann sum with the 4 subintervals indicated by the data in the table. Feel free to try part B out and message me your answer in the chat. Just for reference, the Riemann sum notes is on slide 10. There is a diagram on slide 11 that may help you with this question. Let's see what the solution for part B is. Here's the solution for part B. We're using a right Riemann sum with 4 subintervals indicated by the data in the table. Let's look at the data first. I'm going to screenshot the data and put it in the chat. First of all, we put 2 pi outside because it is just a constant both way outside. So it does not interfere with our calculations. We have 4 subintervals, so first one, second one, third one, and fourth one. They're in the form of r times fr times the subinterval width, and we're choosing the right endpoint. So for interval 0, 1, I choose the value 1 for this interval. And for interval of 1, 2, I choose the value of 2. So I'm picking the rightmost endpoint. That is how the solution is. So I pick 1 times f1 times 1 minus 0 plus 2, well, r equals 2, times f2 times 2 minus 1, which is the subinterval width. And then I do the same thing for the remaining ones to get the right Riemann sum set up. And finally, we need an approximation. So I need to actually find the value of f1, f2, f2.5, f4, and substitute them into the equation. And then I can get an approximation running to 3 decimal places. So the setup is 1 point, and the final approximation is 1 point for part B. With that solution, we still need to do part C. Is the approximation found in part B an overestimate or underestimate of the total mass of bacteria in a petri dish? Explain your reasoning. Feel free to spend around 2-3 minutes to do this. And message me your answer in the chat on whether you think it is overestimation or underestimation. You can also briefly explain your reasoning in the chat as well. Further information is on slide 18 if you need to take a look. Nice, I see some very good answers in chat. So let's go over this. First of all, let's read the scoring notes for part B. I should have done that earlier, but here are some scoring notes if you're interested to check your answer for part B. So for part B again, it's 1 point for Riemann sum set up and 1 point for approximation. And interestingly, simplification of the numerical value is not required to earn the second point. So you can keep the expression like this and you'll get your full point. So it is suggested not to simplify. If you do, then you need to round to 3 decimal places or keep it like this for now. You can read this through afterwards if you're interested in this, in the details running it. But let's go to part C. Part C, we need to use the product rule, first of all. So we have FR plus R times the derivative of FR. There should be a times 1 here, but it is not written because we usually don't want times 1 here. This is because the derivative of R with respect to itself is 1. You see from the table that the function is strictly increasing. So it goes from 1, 2, 6, 10, and 18. So it is non-negative and increasing. This means that our derivative is bigger than 0. So this means that the integrand is strictly increasing. So the right Riemann sum approximation is an overestimation. Since we have a strictly increasing function, and we're picking the highest point, which is the right endpoint out of all points in the subinterval. So we're definitely going to have an overestimation. And we can also check the scoring notes as well. Detailed information on how to implement. For the second point, the response might explain that RFR, which is the integrand, is increasing. So the right Riemann sum is an overestimate. And the response attempts to explain based on left or right Riemann sum. From part B, there's no points, unfortunately. That. Let's go to definite integrals now. We have already seen an example of definite integral. But here is the definition of area under the curve. So when I have infinite number of some integrals, it is going to be equal to the area under the curve. It is non-negative because I want the area to be at least positive or 0. But a definite integral is a net sign area. So if the function is above the x-axis, the area is going to be positive. If it's below, then we are going to have negative area. This is a property of definite integrals. So the definite integral is equal to the Riemann sum with infinite number of sum intervals, provides the limit exists. And if the limit exists, then the function is integrable on the interval AB. Those two information are important when we're trying to convert from one format to another, because we have two formats. Delta x is b minus a over n. This is reasonable because our total interval is from a to b, and I have n subintervals, so I should divide by n. And we generally use regular partition, so I have the subintervals have equal widths. It makes our calculations easier. And for xi, it equals to a plus delta xi. This is also reasonable because it is the i's value. So we depend on this equivalency and those two equations to change formats. Finally, we have fundamental theorem of calculus 1. If fx is continuous over interval ab, and the function fx is defined by this, the integral from a to x, notice that our upper bound is a variable x, ft dt. Then the derivative of the capital F function equals to the lowercase f function over ab. This means that any integrable function has an antiderivative, and differentiation and integration are inverse operations, because this means that fx equals to d dx, which is the differentiation operation, integration operation from a to x, f to dt. So if a function goes through integration and differentiation, then it will become itself again. This is what this means. So differentiation and integration are inverse operations. They cancel each other out. This is a fundamental theorem of calculus 1. Then we're going to have some properties of definite integrals that we can use. First of all, if the limits of integration are the same, then it contains no area, which is 0. When the limits are reversed, then we need to place a negative sign in front. The integral of a sum is the sum of integrals, so we almost have the sum and difference rule almost everywhere. It is in limits, derivatives, and also integrals. Then the difference rule for integrals is very similar to the sum rule. So the integral of a difference is the difference of integrals. And we have the constant multiple rule. This also is very common, so I can pull the constant out, like this. And for the last rule, for a definite integral from a to b, I can change it to that, so I have from a to c and then from c to b. Interestingly, even if the formula normally applies when c is between a and b, the formula is true for all values of a, b, and c, provided fx is integrable on the largest integral possible. So we can have any value for a, b, or c in this case, but the function has to be integral in the first place. As usual, when you talk about the relation between continuity and integrability, so for example, we have a jump discontinuity here, so the function is discontinuous at x equals to 5. However, it's still integrable, because if you check the area is still perfectly defined. The jump discontinuity does not affect the area. So the area is still this. So it is still integrable. This means that integrability does not imply continuity, but continuity does imply integrability. If a function is continuous, then you definitely have an integral. The area under it. You define antiderivatives, which are useful later for calculations of definite integrals. So antiderivative is a kind of reverse of differentiation. Function f is the antiderivative of the function f if the derivative of the capital letter f function equals to this lowercase f function for all x in the domain of f. Watch next slide, we're on slide 13. We have antiderivatives because we have the fundamental theorem of calculus part 2, which is also evaluation theorem. If f is continuous over interval ab and fx is any derivative of fx. This is because we can have multiple antiderivatives. We really have a constant with integration at the end, because the constant does not affect the derivative. And this formula is very useful to get the exact value of a definite integral if we can find the antiderivative. So it equals to fb minus fa. In this case, it is capital F because it is the antiderivative. If we can find an antiderivative for the integrand, then we can evaluate the definite integral by evaluating the antiderivative as the endpoint of the interval and subtraction. Do subtraction to get the value. Example, but I'm going to skip through it because I don't think we have enough time. Let's go straight to those antidifferentiation rules, which are quite important. On the left side, I have a list of differentiation formulas, and on the right side, we have a list of indefinite integral, which is another word for antiderivatives. So, since they're reverse operations, they're related. Example here, if the derivative of sine x is cosine x, then the antiderivative of cosine x will be sine x, and as usual plus c for the constant of integration. I'm going to take a quick screenshot of this for you, so you can use it later. Finally, to take a look at integration by substitution, which is a crucial topic. We need to select an expression gx with integrand set equal to u. We need to make sure that the derivative of gx is also in the integrand. We can do a substitution into the integral, and then we can evaluate it with respect to u. If we cannot evaluate the integral, then we probably selected the wrong u. Then we can write the result in terms of x by reverse the substitution. We have definite integrals. We also need to change the upper bound. That we want this integral, we want to perform the substitution of gx equals to u. Then I must change the upper bounds and lower bounds to make this correct. Because I'm differentiating with respect to u now, not x anymore. So I need to change it. I personally prefer to get the antiderivative first, and then use a fundamental theorem calculus. So it eliminates the need for changing lower bound and upper bounds. But sometimes you still have to do this. So it's helpful to know. We're going to do some practice problems later in our Kahoot. Some other AB techniques would be using long division to break down complex functions into simpler ones, which makes it easier to evaluate. For example, if we have this, let's say, x to the power 5 minus x to the power 3 plus x, let's say over x squared. We cannot do this immediately because there's no quotient rule for the integrals. We need to use long division to break this down into x to the power 3 minus x plus 1 over x, and then I can integrate each part. And it is integrable because we can use the power rule for integrals. And for 1 over x, we can use the another integration rule to get the natural logarithm function. Sometimes we need to complete the square to change the integrand into a better form. So these are the main techniques in calculus AB. For calculus BC, we are going to have more, but we are going to cover them later. And it's time for Kahoot. The Kahoot mostly assesses knowledge in calculus AB, so no BC things. I'm going to start a Kahoot so we can join. And you do not need calculators, and you can review your notes when necessary. So we have a Kahoot game set up here. Feel free to join. I'm going to copy the link in the chat as well. Please join the Kahoot to test your integration skills. you all for joining. I'm going to start the code in 1 minute. So if you have any technical difficulties, please let me know. Nice, I'm going to start. Yes, there are no BC questions, so that's good. But let's do it. And no calculators are allowed today. So for this question, we are doing an integral, and there's an indefinite integral, so flowing need a plus c at the end. And then we're integrating 1, so it is going to be x, because the derivative of x is 1. Since we're not doing derivatives, it is not 0, unfortunately. And by the way, for people who just joined, you can still join by clicking on the link. We still have plenty of questions left, since we just started. I'm going to wait for 1 minute just for more people to join, and then we will continue. In the meantime, feel free to take a look at your notes about the integration rules, because we're going to use them quite often. Okay, let's continue. I'm going to go to the next one. Thank you all for joining. Yes, for this one, continuity implies integrability. Because continuous functions definitely have an area on input. And as in the slideshow, we talked about that integrability does not necessarily imply continuity, because some functions with jump continuities can also have an area under the curve. Let's go to the next one. Oh, that's very fast. Yes, integrability does not necessarily imply continuity. So this limit is false, unfortunately. Because the same limit says that integrability implies continuity, which is incorrect. Let's go to the next one. Wow, that's also very fast. Yes, the correct answer is the green one. If we integrate each term separately, we'll get the green option. The red option is missing a plus c, so we cannot select that. But it is correct with if we add a plus c. Next, this one is a bit tricky. So let's take a quick look. First of all, we have 3 here. If we integrate, we're going to get positive 3x, which all of the answers have, and all the answers have plus c, which is correct. If we integrate negative 3x, we're going to have negative 3x squared over 2, just like this, because I'm going to increase the exponent by 1, and also over the same exponent. So this part is also correct. So we can eliminate option red, because it doesn't have over 2. The most important thing is how to integrate 4 over x squared. It might be better if we convert into negative exponent form, because the power rule is in terms of exponents. So if you have negative exponents here, it is 4 times x to the power negative 2. So if I increase the exponent by 1, I'm going to have x to the power negative 1, which is why it is in the denominator. We still need to make it over the new exponent. So it is power negative 1 over negative 1. That's why we have a change of sign here. Because the over negative 1 changes the sign from positive to negative. That is the reason for the green answer. Be careful of these little details. Let's still go to the next one. Yes, this one is also good to convert into rational exponent. So this one is x to the power of 1 over 3. This means I need to increase the exponent by 1, so that's why we have the exponent of 4 over 3 in each answer. I need to, so we have x to the power of 4 over 3, and again over 4 over 3. So that's why we need to switch the fraction around. So it is not just like 4 over 3. We need to switch order of 3 over 4. Because it is x to the power of 4 over 3 over 4 over 3. So we need to inverse the fraction to get the correct answer. So that's why the full option is not correct. And the yellow option is also not correct because it misses a plus c, which is needed for antiderivatives. Look at the next one. It's also interesting. So those integral questions are a bit tricky because it is easy to just mess up a single point because we have all those fractions. This one is a famous example of U substitution. I can do a U substitution of U equals to 7x plus 4. I need to, let me find the word first. U equals to 7x plus 4. The integral we want to get is this integral. I do a U substitution. And I know that du equals to 7 dx because the derivative of u is 7. This means I need to pull 1 over 7 out. I also need to pull the 8 over 5 out first. That's a constant, so I can pull it out. And then I have 1 over the square root of u du. This part is 8 over 35. And I can evaluate this integral. This is technically u to the power negative 1 over 2. So I'm going to have 8 over 35 times u to the power of 1 over 2 over 1 over 2. And as you know, over 1 over 2 is equal to times 2, so it's 16 over 35 u to the power of 1 over 2. U to the power 1 over 2, I can reverse the simplification. So it's basically times the square root of 7x plus 4. That's why we picked this answer instead. And again, for C. So we can use a U substitution for this Kahoot question. And for people who just joined, you can still join the Kahoot using the link mentioned. So this is an example of U substitution and power over intervals. That, let's go back to the Kahoot and let's go to the next question. We still have a lot of challenging problems left. That's quite fast. But let's take a look. It seems like we're confusing the sign here. The correct answer has a negative sign, but the yellow option has a positive sign. So I think we're doing the U substitution correct. But the issue is that the negative cosines. If we take a look at the integration formulas, that is indeed true. So we have a negative sign in front of cosine x. That is the origin of that negative sign. And I'm going to copy the image of those integration formulas in the chat, so you can refer to them later. This is just a small negative sign issue. And for people who just joined, you can still join the Kahoot using the link mentioned. The game pane is at the bottom of the screen as well. So here's the Kahoot link. We still have 9 questions left, and they're going to be even more difficult. So it's a very good practice. I will continue in 30 seconds. Okay, 30 seconds now. Let's go to the next one. Interesting. I think we should take a look in the slideshow. Well, correctly, this should be the integral here. 9/4 for x plus 1 to power 3 dx. We can do u substitution. Plus 1, sorry. So du will be equal to 4 dx. First of all, I need to pull the constant out. 9/4 out of this. And then times 1/4. We have this huge integral. Power 3 du. This part is 9/16. So I have 9/16 first of all. And then this is u to the power negative 3. So I must have u to the power negative 2 over negative 2. Because of this, I will have negative 9/36. Sorry, 32. 9/32. U is 4x plus 1. And it is negative 2, so I need to put it in the 4x plus 1 to the power of 2 in the denominator. And plus C, and that is the yellow option. So this is the whole process of this U substitution. Let me check the blue option again. I think I made the blue option if you didn't account for the over negative 2. This seems like a common trick option. So keep in mind that for power rule, we're going to have a fraction over the exponent. So in this case, it's 9/16, and then times 1 over negative 2. That's the origin of this negative sign, and also the 16 changes to 32 for this one. But anyways, let's go to the next one. Let's take a look. Most of I choose the right answer, which is the green option. The blue option, we have 36 as the denominator instead of 18. If we choose the blue option, there might be some error in the process dealing with constants. For example, you might forget the 2 here. 2 in the numerator, which might cause this. But I think we still did the process right. So be careful with the small details. Let's take a look. So I think we all choose the correct answer. That's very good. So just for reference, this is also a U substitution. We have U substitute 3x squared plus 3. And then we have negative cosine. And we have constant due to 3/2. And also, we also need to multiply to change dx to du. So the yellow option is correct. And congratulations for getting it. Congratulations on getting them correct. Most of us choose the blue option. And it's hard to see directly because this is a definite integral. But if you want to do a use substitution, I would pick to substitute the exponent 3x power 5 minus 2. Its derivative would be 15x power 4. So I need to multiply by 1 over 15 on the outside. That's part of the reason why we have a large denominator. And then for the substitution part, we have e to the power negative 2 here. That is the kind of the only difference between those two options. I'm going to take a quick look in the slideshow so I can write. going to take a screenshot first. Excellent. So du equals to 15x to the power 4 dx. This means that I can, first of all, multiply by 1 over 15. And again, the constant, original constant inside, which is 9 over 5. This gives you integral. Let's get the antiderivative first so I can worry about the definite later. It is e to the power of u now. And 15x to the power 4 dx gets changed into just du. So since this is e to the power of u, it is, I can erase the integral sign and change u back to this, but plus c. So 9 over 75 plus c. So 9 over 75 is 3 over 25. So it's 3 over 25 e to the power of, let's just keep it as this, plus c. When x equals to 0, we have e to the power of negative 2. We have this. When x equals to 1, we have 325 e to the power of 1. So just this. In the options we have the option should be the difference between those. So basically e minus e to the power of negative 2. So that's why the answer is in the form of 325 e to the power of negative 2, and then e to the power of 3 minus 1. This is because this is equal to e, and this is equal to e to the power of negative 2. We have a short time, so I have to move on to the next one. But we're still using u substitution. Let's go to the next integral problem. So let's go to the next part. it seems like we have a pretty even distribution of answers. And this is a challenging integral, first of all, because it involves some inverse trait. First of all, it's definitely not arcsine because it is in the form of x something squared plus 1. So it should be an inverse tangent or arctangent integral. So not the yellow option or the green. This distinguish between red and blue is a denominator. So here, when you do the u substitution, we should choose to substitute e to the power 6x minus 2. Its derivative will be 6 e to the power 6x. That means that I need to multiply by the 1 over 6 before the integral to even it out, so I can change dx into du. That's why I'm going to divide 7 over 9 by 6, which is the origin of this 54 denominator. So this also involves some chain rule. So please don't forget the chain rule. We are still doing the chain rule in integrals too. Let's go to the last question. So first of all, we have, by the first look, I see e to the power of arctangent for x. So I will try to do use substitution with the arctangent. But we need to make sure that its derivative is also in the integrand. And I think it is, because we have 1 over 1 plus x squared, but we still need to factor out the 8 here. If we factor out the 8, I will have 1 plus 128 divided by 8. 16. So if I factor out 8, I'm going to get 1 plus 4x bracket squared. And we have 5 over 8 on the outside. So let's write it quickly. Let's write down quickly. First, it's going to make our job easier. This is perfectly fine. So I'm going to use a u substitution. And du will be equal to 1 over for arctangent, so 1 over 1 plus 4x squared. And don't forget that we need to use a chain rule. This might also make you choose the other option if you forget the chain rule. The chain rule we can multiply by 4, so I'm going to put this 4 here. So the integral will be 5 over 8 on the outside, and then 1 over 4. And then the integral of e to 5 over 32 e to the power of arctangent 4x plus c. That's the result. That's the last question. And you might choose the green option if you forget the chain rule. Because we have 4x inside the bracket, we need to apply the chain rule. So derivative also needs to multiply by 4. So that's why we need to multiply by 1 over 4 on the outside to cancel out. So this is this question, and congratulations for getting those correct. The last few questions are very challenging to complete. Congratulations, and thank you all for completing this quiz. I'm just going to copy the Polyg link so you can look at that screen later. You're welcome. Nice. And I'm going to use the cosine for them. So if you're taking calculus BC, I'm going to briefly go over the BC topics in the next few minutes. But if you're in calculus AB, please fill out this survey. This will make me improve my lecturing skills, and I greatly appreciate any feedback here. Let's take the next few minutes to go over the BC topics. First of all, integration by parts. This is a very useful formula to solve some complex integrals that might look like a product, If we cannot use substitution directly to get rid of it, then we might consider integration of parts. It consists of this formula. We want to pick the correct u here to make this work. Because some inappropriate choice of u might make this break down, and it will create an even more complex possible integral here. So we should only use it when v du, this v du integral, is easier to solve than u dv. The guesswork is really, I want to pick u as logarithmic first, and the inverse trigonometric, algebraic, which is basically polynomials, trigonometric, and exponential. So this is the order of choice of u. This is a general strategy to make this work. I'm going to skip through the diagram for Q, but they're here. So feel free to look at the slideshow later to check their solutions and their scoring dynamics if you have any. And then we have linear partial fractions. First of all, we'll do a long division if the degree of the numerator is larger than the degree of the denominator. And then I can do this partial fraction decomposition. If the denominator can factor as those products of linear factors, where each linear factor is distinct, and the BC exam only tests distinct linear factors, so you only need to worry about this case, then it's possible to find constants a1, a2, and an satisfy this equation. Breaking down this fraction into some partial fractions makes it easier for us to evaluate integral, because each term is easy to evaluate. We can use a u substitution for each of them. For improper integrals, if we have infinity or negative infinity, or upper bound, lower bound, I can take the limit. If the limit exists, then we say that integral converges. If the limit does not exist, then we say that this improper integral diverges. So for both equations, we take limit, and for the most complex one, where we have both infinity and negative infinity, then I can pick 0, which is often the most common choice, or I can also just pick a. So I break down into two integrals, which is one of the properties of definite integrals, and then I can go back to this formula to calculate. So the third one is the most challenging. We need to make sure that both of the integrals converge. If one of them or both of them diverge, then this integral diverges. Yeah, if the limit exists, then it converges. If it does not exist, then it diverges. I'm going to leave the example for Q here. You can take a look later, and I already have the solutions on the slideshow. And finally, to the last section, thank you for all those resources that I used to create the slideshow. There are also very helpful resources you can use, including course exam description, the OpenStack textbook, Khan Academy integral calculator, some exam FRQs, decimals, and the TI-84 calculator, and the overlay for the latex. I also provide a list of additional resources. And again, please take a few minutes to fill out this survey, which is already in the chat. Your feedback is greatly appreciated and will help us improve our lectures. You only need to fill out the required parts. And for optional parts, you can fill it out if you like. So please take a few minutes right now to fill out this survey. And I'll be happy to see your responses and adjust my lecturing. You can ask any questions you have. I think I'm going to send the site link so you can access the additional resources on the back. And the recording should be uploaded later today. We have the question, what are the best resources to learn more about calculus? I have used on the back. So they're very helpful for me, at least. They're on slide 53 and 54. The most helpful ones that I have is first of all, the OpenSci textbook. This one is linked to integration because we're talking about integration. But this is only volume 1. There are 3 volumes in total. Khan Academy also have some nice videos if you want to watch videos instead of reading text. And we also have Post Online Notes, which is also kind of a textbook thing. Those 3 are helpful if you're studying calculus in general. They're helpful even if you don't study AP calculus, or just calculus in college or high school or university. They're all very nice. If you're taking AP calculus, then it will be helpful to look at the course and exam description, which is CED, and some of the last year's exam overviews to prepare. AP Classroom should also have some daily videos if you register for the exam. And if you take the course, your teacher should give you more resources. I didn't use YouTube videos, but I think there should be some nice YouTubers out there for calculus videos. Nice. And please fill out the lecture feedback form if you haven't also already. And have a great Sunday. I'm going to stop recording now.